Rohit Girdhar is a big guy. That author Rohit Girdhar. Oh, he wrote a lot of papers. Yeah. See if we can run it. They should. Yeah. Do you know him? No, on I searched. Did a. His Junaid the modern.
Yeah, all
Inca Docker, Mirror Docker. I think I'm getting. I need to close this browser. It was one-sided. Okay. All right, guys. We are going to do ImageBind, one embedding space to bind them all. This paper is, again, it belongs to the class of multimodal learning, and it is a good one to start. It's been now 31st March. It's been a couple of months old now, right? And much has happened since then. But it's a simple paper with a neat idea that works. And therefore, that is its virtue. The basic idea in this paper is that if you, and we talked about it in the morning, that let's start with CLIP. If you remember, what does CLIP do? Given an image and given some text, right? I and some text, let me call it the modality of text modality. You know that these two go together if you scrape it off the web and you're lucky, right? So on the web, you have alt, image with the alt tag, img src is equal to the image file, I, and alt will be hopefully the text, whatever text is associated, the caption. It doesn't quite always work because people sometimes skip the caption tag, but even when they do it, they typically do search engine optimization. They tag in the company's name, or they just stuff it with all sorts of keywords to bring Google traffic to their site. But so given all those imperfections, Facebook was still able to scrape a large data set. That was moderately effective. And if you remember, one of the achievements of Blip was that you could use it to clean the data set that was used to train CLIP. So Blip was self-referential. It cleaned its own data set and retrained itself. Right? So that's the history. We have covered that in the previous course. So here what we do is, we know that if you have a vector space, let's say that this is your latent space, you have a way of doing semantic embedding of a text, of an image and a text into this space. Are we together? You can associate text to this image. And the loss function, if you remember, what was the loss function? You use a triplet loss, contrastive loss. Well, it's not just contrastive loss, but it builds upon that. But the basic idea is that the loss function is the distance between an image, a text, relevant text, let's say, or actual caption, and something random. Like you want to minimize this distance and maximize, and therefore with a minus sign, distance from image to random. So if you were to do that, train with this loss function, and how would you, so this begs the question, how would you first convert a text to vector? How would you convert text to vector? We have been doing that, right? For example, we have been using sentence BERT and so on and so forth. And so the next step is, how do you convert images to text, to vectors? We convert images to, because for example, use the same thing, break it up into patches, treat each patch as a word or a token, right? VIT, and therefore you can get a vector representation for the image also. And then you apply contrastive learning to this, and therefore you come up with a semantic embedding for images. Right? This was the gist of the clip paper, and then you can do it better with blip and so forth. Now comes this interesting question. Let's look at a modality like audio. Suppose we take audio. Okay. What does an audio file look like? It will be some squiggly along the time axis, isn't it? And there will be different frequencies, different amplitudes and so forth. The frequencies are in the squiggles, amplitude is in the height of this segment. Are we together? Okay. And then this is the time axis. Now, audio signals are usually studied using many ways, but one of the ways that you can study it is by doing something called a Fourier transform. Yeah. And in fact, short interval of Fourier transform. You take a snippet of that, a little part of this thing, and you take the Fourier transform. If you take a Fourier transform of a little bit of a signal, or what do you think you'll get? You'll get all the frequencies, the harmonics that make up that segment, isn't it? And those harmonics, they change, they keep moving as you keep moving forward in the slices. So let's take one particular slice. In this particular slice, you will get frequencies. Each of these frequencies will be of different intensity, isn't it? So what you do is you put a point there based on the intensity of it. If it is, so you can imagine that you will get up with some different frequencies, a histogram of the frequencies. Are we making sense? Now what you do is you convert the histogram into some sort of a color map, right? Red for big or something like that. So somehow don't keep it as a histogram because it's eating up one dimension, but change it to the color spectrum. Make it a color or make it an intensity, right? Something like that. And so what you will end up with is that for each point in each segment, let's say for this segment, you will end up with a column of color at different frequencies, F1 all the way to low to high frequency. You will imagine that these are segmented. You would imagine that each segment would have a different level of color and intensity, right? That's it. Now, as you go from segment to segment, this is your time axis. This is your frequency axis, right? What you will end up, this is very sort of, I mean, obviously, if you come from signal processing domain, you may cringe because I'm oversimplifying things. But basically, this is your, what is this called? Anyone? It's your spectrogram. Spectrum, the frequency part of it. How do you go to the frequency domain? This is your Fourier transform. You do a Fourier transform. Now there's some technicality to the implementation of that short interval Fourier transform, but we'll come to that. So you get a picture like this. If I give you an audio signal, would you agree that it will become a picture like this? Now on this picture, this is called a spectrogram, but usually you tend not to use it directly because the human ear responds to frequencies differently. Some frequencies we don't hear at all. There's only a range of frequencies we hear. And then within the range of frequencies, it turns out that we are extraordinarily sensitive to shifts of low frequency. So when I'm talking to you, small frequency changes, it will have an effect. On the other hand, if you go to the very shrill end, like a whistle, right, then small changes in whistling we are not as receptive, right? Very shrill frequencies or high frequencies. Right? All we can feel is high frequency. Right? So what happens is that our sensitivity itself has a log scaling behavior. Right? You want to sort of, what you want to do is squish it up. The things that are at low frequency, you want it to be more dominant, because subtle changes mean something. At high frequencies, it doesn't mean as much. So you need to expand it longer. Yeah, that way. And so that is called the MEL transform. So you apply a form of transform to it. And at the end of it, what you end, this is again very oversimplifying things, because there's beauty and there's a subtlety here, but this is your MEL spectrogram. Spectrogram. Now forgive me if I butchered the spelling, but I think I got it right. Spectro. Oh yeah, RT is reverse. I knew something was wrong. Spectrogram. Are we together? This image, but what is this MEL spectrogram at the end of it? It's an image, isn't it? So when it is an image and you are thinking multimodal embedding, now can we do embeddings? We can. What can we do? We can take yet another vision transformer, open up its weights, again do contrastive learning, keep the image fixed, because image we have learned how to embed, a genuine image, picture of a cat. But the meow of a cat is a sound file, which becomes a MEL spectrogram. And what can we do? We can open up its weights, and what we can do is contrastive learning, such that the meow of the cat lands where the image of the cat landed in the vector space. You see how easy it is, right? And then, of course, as a random, like because you're doing contrastive learning, you can take the meow of a cat, right? The image of a cat and the image of a house, right? And obviously, there should be a vast difference between the sound, the meow, and the house. Houses squeak, they don't meow, right? Things like that. Are we getting the idea? So now we got sound down, right? Let's look at, so now we can do a joint embedding of text, image, and audio. And so one beautiful thing is that image is in some sense the hub, not text, image, because quite often every other modality is somehow associated with image. You write something, you almost feel compelled to put an image there, right? If you do PowerPoint, perhaps it contains more images than text. Right? Images are everywhere. Well, images, eyesight is perhaps the most dominant quality of human beings. We have far better static vision than I think most other species, right? So you have the image, and going back with the dictum that an image is worth, a picture is worth 1,000 words. It just shows how compellingly we respond to images. You take that, you take text. We just got audio into the mix. We can align audio to image. Why? Here's a cat picture and meow, right? So we can do joint embedding. Now you say, well, that looks good. While we are at it, let's take a thermal image. A thermal is just an image. It just is taken at a different electromagnetic spectrum. The sensors are at different things, right? And by the way, most light sensors, they also read thermal images. I don't know if you know. So when you get these high-end cameras, or most cameras, digital cameras these days, the manufacturers actually have to put a thermal filter in it. Why? Because otherwise the thermal picture will show us without our clothes, right? So you have a thermal filter there.
So it can be used as a military.
It is. So I'm told, so this is how I was told that most of these devices, the sensor spectrum, it's not like that there's a hard cutoff. Suddenly at beyond red, it won't go to infrared.
Wow.
Right? So they have sensitivity there also. So you have to explicitly put a filter. Right? So there's thermal. So thermal image, therefore, is an image in some sense, right? Then, so thermal is taken care of. Then you can go to depth sensor, maybe sonar things, and you bounce back and what you reconstruct, a picture, isn't it? Picture is picture, doesn't matter how you reconstructed the picture, isn't it? So depth. So you realize that once you get your image thing down, one second, a lot of other things sort of become freebies after that. You just need some way to convert them into pictures. So depth echoes, you need to convert those echoes into a picture, and the technology has existed for a long time. Right? Go ahead, Prakash.
So in the depth, I saw some example while reading this paper. The depth sensor, when it converts into the 2D image, we lose that, right? In the image.
Yeah, the way they do it is at the grayscale. Things that are further away and things that are nearer, you use the different grayscales for that. So once you know that it is grayscale, you can tell which is near and which is far. That's it. And then there is the next one is the IMU data. Now, what in the world is IMU data?
Gyroscope and
yeah, the accelerometer, gyroscope, etc. It is international inertial measurement unit. And it has its 6 degrees and 6 channels. So it's just images with more channels in it, right? Signals with more channels in it. That's all it is. Think of it as 6, like for example, if you're looking at a gyroscope, you can almost think of it as a 6-channel audio signal, right? As the car is bouncing around or the object is bouncing around, you're getting the yaw, the pitch, the forward and the backward, movements and so forth.
surround sound.
Yes, sort of like that, yes. So that itself can be converted into an image. So
is that an audio thing or is it the whole, the audio as well as the visual?
no. So like for example, acceleration data. You go from here to LA. So you accelerate, you deaccelerate, you accelerate. But at the same time, your car is doing, as you make sharp turns, the pitch and the yaw of the car, the forward, like you hit the brakes and your car goes like this. You accelerate, your car goes like this.
So is it, okay, it's a whole video of the situation or is it an audio of the situation?
No, just the numbers.
Or just the numbers, okay.
Yeah. Numbers. So it just says acceleration at this moment is this goes up, goes down, goes up, goes down. Cop is there, slow down. Okay. Right. So things like that. Yeah. So that's the data. So all of that data, you realize that once you figure out how to convert audio into picture, the rest begin to fall in place pretty quickly. Isn't it? Similar techniques. Then comes the video. Video, of course, the way these people did is nothing high tech. What they said is over 2 seconds or 3 seconds, I forgot what. They just take 2 frames. So one image has 3 channels, RGB channels, and then add 3 more channels to it for the second image. Right? So that is again an image, and images we know how to make into vectors. So what do we learn? This paper therefore becomes using 6 different modalities. Actually, when you think about it, it is like literally putting the last block of the puzzle in place. Yeah. Different researchers have built all these different pieces, isn't it? And you come and put the final piece in place and you say, yay. Right? But it's still it's great work. I mean, this is how research works. Right? There comes a moment where you realize that all the pieces are in place. You just have to put them together.
Like integrating the code, you said. Different, everything is there. Integrating the code.
Integrating the code, exactly. Go ahead.
So, so for example, in project 1, we did the semantic search, right? So, text has a certain semantic meaning to it, right? And here you describe audio spectrogram, which you said basically converting audio to image and mapping it to a space. Now, how's this marriage of the text semantic meaning vector space to an audio's meaning? How are the 2 brought on the same scale?
Okay, so I'll say that. Prashant Yadav has asked this question. How do you marry the fact that the text has clear meaning? Images we brought into the fold. But audio, how do you do that? Well, it's very intuitive. What if you're literally reading the text and speaking it out? So then obviously the text and the word has literally the same meaning. But now let's take it a bit further. Suppose you see an audio of, like I took the example of a youngster swishing by you at 120 miles an hour, right? So what is the audio? You would see the Doppler shift, right? The Doppler sound, the frequency of that increasing and then decreasing. Literally, you can see it in the spectrum, in the frequencies. So you get a unique audio signature from that. It will have a unique signature. And you can see that, by the way, these Mel spectrograms are very beautiful. There's a car misfiring, a gunshot. All of them have unique signatures. You and me speaking, we have different signatures, even when we are talking about the same thing. It captures our accents and so on and so forth. So now comes the thing, a car goes by and you have a picture of a car swishing by, you see the blurry trail of a car. What do both of them convey? A speeding car. So where you could therefore train the audio encoder, the spectrogram encoder, the visual encoder, actually the real visual encoder from the Mel spectrogram, to adapt in such a way, learn from the loss function in such a way that it lands next to the picture of a car swishing by. And therefore, semantically, I've aligned the meanings of three modalities now: audio, video, and audio, image, and this. And from image going to video is very easy. You saw that literally have a video of the car swishing by. Okay. Now comes depth. Likewise, if you have a depth image, you can imagine that the car was far away, right? Especially, and now it's coming at you, and then it's going away from you. Yeah. So you can align things. You can basically start aligning things together, right? Meaning wise. But the beauty of this is from the fact that, let me move this picture. Why is this become so big? Yeah, sorry, guys. I need to give me a second. I seem to have
Some background noise.
Give me 1 second. I seem to have lost the ability to. Okay. All right, I'll leave it. Something is. Are you guys able to see my screen?
Yes, yes, the paper.
Oh, the paper. Yeah, excellent. So this is something weird is happening. I will actually close this and reopen it, guys, and give me a second. ImageBind, OneNote. Yes, much better. So now let's read this paper. ImageBind. Why am I getting 2 copies of the paper? I have no idea. We'll ignore the second copy. Yeah, okay. So let's read this paper. What this paper says, guys, do you get the main idea of this? We can do joint embedding therefore. Now, what are the virtues of the joint embedding? We are using it. So this works really well with retrieval. I can bark, right? And as search results, I should get dogs, isn't it? That is one. So you can use it for retrieval task. You can use it for classification task. What can I do? Suppose I have a chirping of a bird and the bark of a dog. I want to classify it between birds or dogs. I claim that the moment you have this embedding, you don't need to train a classifier, an audio classifier at all. You can actually use this joint embedding to do the classification. How can I do that?
this ImageBind?
Yeah, all you need to do is take this bark, and then you know that it will land somewhere in the vector space. Now just create a query that says, this is the sound of a dog barking, and another sentence, this is the sound of a bird chirping, right? Encode this into the latent space and see it is closer to which of the two sentences or their vectors, isn't it? So if it is closer to the dog barking, you heard a dog bark. You see how simple it is. So therefore you can do literally classification, and this is what you call zero-shot classification. You didn't train a classifier at all. It came as a freebie. Okay? A zero-shot usually means freebie. So after all, there is such a thing as a free lunch, right?
Asif, I have a question.
Go
So
ahead.
similar to the, the clip embedding of symmetric cross entropy, where you maximize the similarity of the bark sound and the picture of a barking dog.
Yeah.
It-
Yes. You take the picture of a barking dog and then you train it together, cross-train it together. During the training process.
Hey, Asif, I have a question.
Sure.
If you look at the bottom last two sentences of the introduction, it goes over the two-dimensional thing, but then it says the video audio embeddings cannot be directly used for image text tasks and vice versa.
Mhm.
So does that sentence mean ImageBind is not good for videos, or?
No. It is actually critiquing other people's works. It's saying that in the prior work that has been done, if you look at this sentence, the broader context is, hang on, give me 1 second. Read this. Recently, many methods learn image features aligned to. These methods use a single. However, so it is pointing out to the limitations of those methods, not its own method that it's going to propose. Right. So what it is saying is, think about it this way. You have a fundamental problem, right? Suppose I have a video, VI, and an audio, EI. How would you create a joint embedding in a vector space? You don't know, right? Now, you can try some things. If you build a model only of this, it will be just a very specialized model of these two. It won't be text aware or image aware. But if you use image as a hub and you surround it, which is the idea that these people have, and everywhere, audio, video, text, modality, all the other modalities, because they all are associated with image very often, right? Therefore, it's very easy to align them into a joint embedding, into a common embedding.
Thanks.
Right. So,
Asif, one question on this different audio or different persons, let's say Asian or Indian or different audio. How does it convert and refers the same image?
so suppose you have a person talking and you have an audio signal. It's a person talking at the audio signal, and you have a picture of the person, right? It's a little harder because the picture is just static.
Yeah.
So that is not a good training data.
No.
You take things where they are related. Right? So, all right. So now let's read the paper. But before we read the paper, let us look at the possibilities. Do you understand how you can do classification? But you know, vectors, one of the good properties of a vector is you can do vector arithmetic, right? So what you can do, and this is the thing, if you look at the item number 2 here, first of all, look at the row number 1, cross-modal retrieval. You can give it the crackle of a fire, and in the search results, you can get images and videos of the fire. That makes sense? You could get depth pictures of a fire, how far away it is, any sense any depth image associated with a fire. And you could get text associated with a fire crackling and so forth. And you see the results. Joint embedding produces relevant results. Likewise, a baby cooing, right? You see all of these descriptions come back. So that is a cross-modal retrieval is the core benefit that comes. Everything after that is a consequence or a corollary of that, right? Let's look at the number 2, embedding space arithmetic, because you can add and subtract vectors. Suppose you take the vector of a bird, and then you take the vector of waves, right? You could do it by just giving it sound of a wave and the picture of a bird, or you could have given it the word bird. And then you say, take these 2 vectors, add them up, and search for the joint for the A plus B. Suppose the vector is C. C is A plus B. C is bird plus waves. Search for the C vector. So what will it do? What will it be closest to? In images, it will be close to something that contains both waves and birds, a bird on a beach, isn't it? And you see that.
So for this, like, should we use any tools, or can we just add both the vectors and try to use it?
That's incredible. Incredible. Amazing, isn't it?
Yeah.
But if you think that this is a vector arithmetic or vector so then it can produce a different combinations, right? Different pairing. Like let's say total is 5. So 1 plus 4 is 5, or 3 plus 2 is 5, or 2 plus 3 is 5.
Yeah,
So-
you do have that issue, but all these arithmetic-based systems obviously have this issue that you can do that. In reality, these vectors are very high-dimensional vectors. Remember, you're talking scalars like 3 plus 2, but in a 20-dimensional vector with a unique vector for a bird and a unique vector for a sound, it's very difficult to add up to another final vector and get the same answer by randomly taking a few other. You can come close to it, but it's not as common as it's common. And remember, these are very high dimensional vectors, 768 and so forth.
So does that mean that this is only solving one set of problems, not all?
This is very retrieval.
Retrieval.
This Excel set retrieval and
Excel set.
all the side benefits of retrieval.
Got it.
So for example, as a retrieval task, you can literally give it bird and sound waves. And if there are in your database, in the vector index that you have created, if there's a vector indexing of a bird on a beach, it will find that in the search results.
I see.
Right? Isn't that amazing? Right. And likewise, audio generation. What can you do? You can take a dog, right? And it will generate the picture of her. You can use it to, so generative is a little bit more hard, but let's take it like that. You can give it a vector and say, what does it correspond to, right? Create a dog or a engine, a fire, a rain, and so forth. Right? So let's go through this paper a little bit more carefully because we have a lot of paper to read, but this is the core idea. Are we getting it?
And the ImageBind is just for vector operations, right? Like generation, we would have to use a different one.
No, it gives some, see, all of these are encoders, right? In general, encoders are not that great at generative tasks. A little bit is there, but take it like that.
So, but does that mean that ImageBind operations require their own encoders or their own?
Yeah, that's what they train. Yeah, exactly. They have their own.
That does not, like if I change some model on my search retrieval system,
Yeah.
then this will fail.
Yeah, you have to be careful. Like use one encoder. ImageBind is sort of one encoder to encode them all. I see. Right? And image is the binding, the central element that you use. And in a way, it leverages clip, the like things of clip, open clip, etc. If you want.
Is it as good as individual thing or close to the?
It's pretty good. And in fact, your exercise is to play with it in a project and see how well it comes out. Yeah, but the whole point is not to give you hints before.
Yeah,
So-
so question. You said this is great for classification and retrieval task, But if somebody wants to do a synthetic data generation
Yeah.
based on image or audio, what would be a good way to do that?
Oh, we are literally coming to that topic. So hold off for a little bit longer.
This is actually
When we come to animal, we will be talking a little bit about that.
Okay, thank you.
So generally, let me put it this way: when you have things like this and generative, right? You bring in stronger generative elements, you get better results. So imagine you feed this into a diffusion model. You realize that now you're taking strengths of a generator and the strengths of a retriever.
so the vector that ImageBind gives. How do we, like, the generative model might not be accepting the same vector, right? Like, how do you
Yes, yes, you have to put some glues in between. You have to train a little bit. All of those are there. And that's how so many papers are coming out. Right? All of this. But it's not conceptually, it's not hard. In practice, of course, everything needs GPUs, everything needs effort, everything needs data. So that's that. So we read the abstract of this paper. We present ImageBind, an approach to learn a joint embedding across 6 different modalities: images, text, audio, depth, thermal, and IMU data. Does that make sense, guys? We show that all combinations of paired data are not necessary to train such a joint embedding, and only image paired data is sufficient to bind the modalities together. And therefore, emergent behavior. See, image is the hub of all the other scopes, right? And so what you can do is you can actually go across using a audio. You can retrieve images. Bark, you can retrieve dogs, even though the system was never trained for that or classified. So this is emergent behavior, new behavior that just sort of emerges freely for you. Right?
Zero shot.
Yeah. So
I have a question regarding this vector arithmetic. So it's essentially like mean polling that we are doing.
no,
right?
mean pooling is different. Mean pooling divides by n.
Okay.
This is
This
just
is
adding
just
a plus
addition.
b.
Okay.
So that's that. So we show that all combinations of paired data are not necessary to train such a joint embedding, which makes sense because it's a hub and spokes model. You're not doing every possible combination and training them. And that is the key feature. That it's a much simpler approach. You are not going to create 30 pairs of data, vast data sets, right? Audio and thermal, so on and so forth. You don't have to do that. ImageBind can leverage recent large-scale vision language models and extend their zero-shot capabilities to new modalities just by using their natural pairing with images. It enables novel emergent applications out of the box, including cross-modal retrieval. We saw cross-modal retrieval, right? So composing modalities with arithmetic and cross-modal detection and generation. The emergent capabilities improve with the strength of the image encoder, and we set a new state of the art on emergent zero-shot recognition tasks across modalities, outperforming specialist supervised models. And this is the interesting thing. When you do that, it actually beats sometimes models that were specifically trained for that combination, right? And why would it do that? My interpretation is it's a deeper learning because any information has multimodal representation. And in a way, forcing a model to recognize all of these different representations as being the same thing leads to a deeper semantic understanding of what it is, right? So perhaps that's the reason. Finally, we show strong few-shot recognition results outperforming prior work, and that ImageBind serves as a new way to evaluate vision models for visual and non-visual tasks. Right? So it is good result. And of course, these days it's almost hard to get any paper accepted unless you say that it does better than the state of the art.
Yeah, I'm just imagining a scenario. Asif sir ringing this bell and Asif sir's photo shows support vector class, not
yes,
some other temple or monastery.
Yes, that's true. Yes, that's true. And that is multimodal retrieval. So I will go to the heart of the algorithm with this. You guys have, oh, what happened to the rest of the paper?
Probably that got deleted.
Yeah, okay, so anyway, I seem to be in the right space. A zero-shot classification, I already told you why it happens, right? You can do that. Binding images to modality. So guys, in this entire paper, I believe this is the only equation. So let's look into this equation, right? So what they are saying is something very well argued, simple and simply said. Take this. Suppose I is an image. Are you guys able to see my writing?
Yeah.
I stands for image in this equation, and M stands for any other thing but image. It could be an image also, doesn't matter, any other modality. So what happens is you are doing joint embedding between an image and something else. Means image is the hub, right? So now what would you do? What does contrastive learning say? If I take a query, so remember, what is a neural network? You need one neural network that will take an image I, and convert it into a vector f. So every neural network is nothing but a function, isn't it, guys? It's nothing but a function. And so this is a function that will act on I, and let's call it qi. It is the embedding vector for that image. Are we together, guys? Likewise, so this is your neural net, made up of your transformers. These days, transformers it is. And let's say that you have another modality. Think text, audio, whatever it is, right? And that also is one network, neural net, right? Neural net. So you can think of that also is a function. So it will produce ki. So suppose you have a modality I, some modality I goes in, it will become ki, right? Which will be equal to G of mi. So far, so good, right? And now think about it this way, that if this is true, what do you want? What will the similarity, what is the measure of similarity in high dimensions that works well? Dot product, right? And if they are normalized vectors, it's cosine, right? So dot product and cosine. So that would be this qi transpose ki, right? Another is the same as I write it in this language, qi ki. You notice that I tend to use a slightly different notation for dot product, but basically this is it, right? These two, right? It's a dot product. Dot prod or scale dot product. It could be the cosine. Pick one. Something. In this case, they are picked dot product. Now, and if it is a normalized vector, then it's the same. Yeah. Then into normalized embedding. So normalized means it is actually the dot product. It is the cosine. It becomes cosine. Go ahead.
So MI is any modality.
Any modality. Any modality.
And I
Data.
of all the images, any possible.
Any possible image is I, and any ith of any modality could even be an image, something like that. Now comes the thing. This is a similarity measure. What do you want to do? You want to maximize this qi, ki somehow, and you want to minimize qi with kj such that j is not equal to I, right? You want to minimize and you want to maximize, right? And so if you think in terms of logics, you remember that dot products can have any sort of values. You always normalize them, exponentiate them, right? So that they all add up to 1. So that's what you will do. You will say e to the qi ki, right, divided by everything else, e to the qi ki, that is one possible pair, and all the things that are not dissimilar, qi kj, over all j not equal to I, isn't it, in the denominator, because that will be all the other logics, right? So let's say that the first one produces 3, the other ones are whatever they are, 3 divided by that. That will make it into a probability, isn't it? and exponentiation makes it stand out. The big guys stand out. Now, you remember there was also temperature. What was the purpose of temperature? Is to damp down, a little bit of damping. So we can bring that in. If you notice that if I scaled it by temperature also, I could do that. By now we are familiar with temperature, isn't it? And you understand how easy the argument is? And what have you reconstructed? You have reconstructed the probability of the right image. Yeah. You want to maximize the probability. For probabilities, what is the loss function that you apply? Negative logs, cross entropy loss, right? Minus log. This is your loss function, therefore. And this equation is exactly the equation that you see here. I'll let you see it. If we did the same thing. You look at the equation that is in yellow and the equation that we created. Is it the same equation? Right? So this is the reasoning, guys. It's a very obvious reason. This is obviously the famous info NCE loss equation, but it has a very intuitive explanation of why it is the way it is. Make sense, guys? That is it. And so this is it. You use this, and then you can have emergent alignment from all sorts of cross modalities. Yeah. Audio and thermal or whatever it is. Right? So the rest of that is details of how you get the data, what you do, and how well it does. Right? And you can see that if you look at these numbers, they are doing pretty good actually. Right? You realize that doing ImageBind actually leads to close to state-of-the-art results and often beating the state-of-the-art results. Right? But I want you guys to, in your project, this is your project, guys, go use ImageBind, keep your other implementation, and compare the results. Are we together? Go compare the results of multimodal search. Go do that. See how well it worked. Right? So you can do few shot classification, right? And so forth. So I'll let you read the rest of the paper. Right? There's more to it, but I suppose that's the gist of it. I would like to move on to the next paper. Go ahead.
Like the MEL spectrogram, are they suggesting anything specific for IMU data or like?
Check it out. There must be. Okay. I didn't look into too much. For me, it was theoretically obvious that you would do something like this, but find out what they do. I would like to know that myself. All right, guys. So that finishes our first paper reading. We'll take a little bit of a break. Then we'll come to LoRa. 10 minutes break makes sense? Right? And LoRa will be a segue into the second half of this bootcamp. Till now, you have just been using models to do your work. Now you'll have to train the models, fine-tune the models. Right? And so LoRa is a good segue into that new territory. And I leave it to you guys to read the AnyML paper. I'll pause the recording here, streaming here.